All right, today I'm going to talk about the subject of strong versus weak saturation. As I mentioned last time, these definitions are something that what the book says and what personally I, from my design experience, and what other people will say are different. But that is how we actually define saturation in a BJT. So if a BJT has a situation where IC over IB is less than beta, as we mentioned last time, looking at our examples, then if this is true in a standard BJT, then we say that BJT is in strong saturation. And a strongly saturated BJT will not amplify. So in effect, a saturated transistor, a saturated bipolar junction transistor, is really useless to us as an amplifying device. However, it is possible for a BJT to be slightly saturated, weakly saturated. Now, in general, you want to avoid, whenever you can, saturation of any type, of any degree. But a weakly saturated BJT will still function. A BJT can tolerate small amounts of saturation, or small amounts of, I should say, a forward biased base collector junction. Or as it's called, weak saturation. And what I mean by that is the base collector junction is forward biased, but only slightly, maybe only by a couple of hundred millivolts. Not enough to really turn the junction on strongly, not enough to have any significant current flow across it, but still forward biased. And in situations like that, what you'll find is the beta relationships still work. So as an example of that, let's look at this circuit. So in this case, we've got an NPN transistor connected to a 10-volt source. I've got a 4.6-volt source connected to the base. And again, let's define our collector, base, and emitter currents for this NPN transistor. It's collector and base flowing in, emitter current flowing out of the emitter. And let's go and let's do some quick calculations for the currents and voltages. So this is VC, this is VE. So what answers do we get for this? Well, if we look at this, we know the transistor has to be on, and the reason for that is if the transistor were off, there'd be no emitter current, and the voltage at the emitter would be equal to 0 volts. We'd have a forward biased base emitter junction of 4.6 volts. That doesn't make any sense. So the transistor must be on. So in this case, knowing the transistor's on and using the constant voltage drop approximation, the CVD approximation, we know that that's going to be equal to 0.7 volts. And therefore, VE must be equal to 4.6 minus 0.7 is equal to 3.9 volts. So in that case, IE will just be equal to 3.9 divided by 3,300. And that will be equal to 1.18 milliamps. And if we assume IC and IE are large, so in this case I'm going to, once again, I'm assuming that the beta is going to be big, like 100, some large value. But if we assume the beta is large, then, as we talked about before, we can say that IC and IE are going to be approximately equal to each other. And therefore I know IC, or I should say VC, is therefore going to be equal to 10 minus 4,700 times IC, using the same values I got for IE, and then VC will be equal to 4.45 volts when I plug in the value for 1.18 milliamps. So looking at this, we note that VBC is equal to, in this case, 4.6 minus 4.45 will be equal to 0.15 volts. Now clearly that is a forward biased junction, but it's only slightly forward biased. Remember, PN junctions only turn on at about 0.6 volts or so is when they start to turn on. So it's forward biased, but it's not really on in the strictest sense of the word, okay? You're not going to have significant current flow across it. In addition, we can go through and I can calculate IB using the beta relationships. Everything works. And again, once again, I assumed IE was equal to IC. There's nothing impossible in this answer as far as the values in this problem. So everything works, the beta relationships work, even though I've got a little bit of forward bias, even though this transistor is actually saturated. So in this case, the transistor is saturated, but not enough to make the beta relationships break down. In other words, this is weak saturation. The base collector junction is slightly forward biased, but I can still get a reasonable answer. The beta relationships still work. Now, this transistor, this weakly saturated transistor, can still function as an amplifying device. So it can still work as an amplifier, but it's not a good idea. And there are a couple of reasons for this. First and foremost is if you are biasing a transistor where it is weakly saturated, you're biasing it very close to the point of failure. Designing any circuit or any system so that it is very, very close to not working is never a good idea. And when you're weakly saturated, you're very close to that. Secondly, any degree of saturation can result in a type of failure that can happen in integrated circuits. And you absolutely want to avoid this entirely. This is called latch-up. Now, how latch-up works is beyond the scope of this course, but it is a destructive mechanism that can result in literally the chip being destroyed, melting, and because of large currents that flow through it. So you absolutely want to avoid latch-up, but one of the things that triggers latch-up are transistors that are in saturation or that are pushed into saturation. So operating in weak saturation is really not a good idea. In fact, it's an extremely poor idea. All right? Well, how do you know whenever you have transitioned from weak saturation to strong saturation? Well, this NPN transistor we have in this example, it will enter strong saturation once VCE reaches a critical voltage that we call VCE sat, the saturated value of VCE. So when VCE falls to a VCE sat value, and this is normally in the range of about 0.1 volts to about 0.3 volts are typical values for VCE sat. The textbook will quite often use 0.3 volts as that threshold. You'll see other textbooks will say 0.1 to 0.2 volts. But what you'll typically observe is once you get down to about 0.1 volts or so, VCE is not going to get any smaller. So think about what's happening here with this design. So for this circuit, I've got 3.9 volts. VC is equal to 4.45 volts. And if I keep increasing the current flowing through IC, if I keep increasing the IC current and the IE current, then what I'm going to find is the value of VC drops until finally VCE is going to hit, like I said, somewhere between 0.1 to 0.3 volts. And at that point, the beta relationships are going to break down entirely. So, strong saturation, just to kind of recap. In strong saturation, our forward beta is going to be less than the actual intrinsic beta of the transistor. So I should say our forced beta, excuse me. So the forced beta is going to be less than the intrinsic beta of the transistor, as we've already talked about. And VCE will be equal to VCE sat. And I want to emphasize this VCE sat value is typically going to be provided to you. You're going to be told what the saturation value is. When you're in weak saturation, then your forced beta is still equal to beta. So your forced beta doesn't change. It's still the same beta as the transistor. And in this case, the collector emitter voltage will be greater than VCE sat. And once again, as I mentioned before, your transistor is still functional. It still operates. The beta relationships still hold. You can still make it operate as an amplifier, but it is very, very close to failure if you design it to be biased in weak saturation. Now, if you look in the textbook, the problems in the text, typically in the text, VCE is equal to 0.3 volts is quite often used for the problems. So VCE at 0.3 volts, the book will typically treat that as the boundary condition between weak and strong saturation. So in working problems in the textbook, that is generally the boundary condition that the book will use. But when the book does this, when it says that VCE is equal to 0.3 volts, the book says it's the boundary between active operation and saturation. So this is what the text will do. Now, the reason why the book says that weak saturation is active is because, as I said, it still acts like an amplifying device. But really, saturation is saturation. If you are forward biasing the base collector junction, you are strictly speaking in saturation. But the book doesn't make that distinction. It considers, as long as the beta relationships work, it considers the transistor being in active operation. But many other people will totally disagree. They'll say it's weak saturation, and they'll also say never bias a transistor in weak saturation. All right? Now, once a transistor is in saturation, and by that I mean strong saturation, there is a circuit model we can use for it. So when we have a saturation model for a BJT, keep in mind the base collector junction is beginning to forward bias. And so we will have this type of model. So we have this diode that represents the base emitter junction. Call that D sub B. We'll also have the diode that represents the forward biased base collector junction. Call this D sub C. And you'll have an ISC times e to the VBC over VT as the relationship base collector voltage versus current. So very similar to what we saw before, the ISE to the VBE over VT. But now we've got different variables, and in this case, we're dealing with the forward biased base collector junction. In this case, IB is flowing into the base. IC is flowing into the collector. And then, of course, IE will flow out of the emitter. So in this case, and oh, I forgot to add this, this will be ISE to the VBE over VT. So I wanted to include, in this case, the proper variables for both the collector emitter current and the base collector current. So in saturation, this diode turns on. We are now adding that to the model for the transistor. Now, if you move into strong saturation, I can make a much simpler model. So in strong saturation, you can actually represent the BJT as really nothing more than a couple of voltage sources. So in strong saturation, the beta relationships have broken down. Now I've got this junction is strongly forward biased, and I've got a voltage between the collector and the emitter, which is going to be somewhere in the range of 0.1 to 0.3 volts, which of course will be equal to my VCE sat value. So you can actually just use that as a very simplified model once you are in saturation, because it doesn't matter what current you put into the base, essentially it's not going to change the value of the voltage between the collector and the emitter. And certainly the base current has no effect on that current. It's really totally non-functional as an amplifying device. All right, so again, when you're looking at these problems, when you're working these problems, saturation for a BJT is never a good thing. And even though the book treats weak saturation and like active operation, it's really never a good idea to ever operate a transistor in any degree of saturation, a BJT. So in this case, certainly whenever I give my exams and give my problems, I'm always going to specify that the base collector junction has to be zero biased or reversed biased. That's going to be the boundary condition, zero biased. I'm never going to forward bias it. It's simply not good design practice. Okay, so having now looked at this definition of weak versus strong saturation, let's work another couple of problems here and wrap up with some DC analysis of BJTs. So let's work the following. In this case, let's work a problem with a PNP instead of an NPN transistor. So in this case, I've got power supplies in plus and minus 10 volts. I've got a 50 kilo ohm resistor in the base leg. This is the emitter, VE. RE will be equal to 2 kilo ohms. RC will be equal to 1 kilo ohm. And this is VC, and this is VB. And in this case, once again, the currents are in reverse direction compared to the NPN. So in this case, IE flows in to the emitter. IB flows out of the base. IC flows out of the collector. And of course, the reason for this is you want the currents to all be positive, whether it's NPN or PNP. All right, so in this case, we're going to say that it is given that beta is equal to 100 for this transistor. So that's given to us, and we want to calculate all of the currents and voltages. So let's do this. All right, so first of all, let's check. What operating condition is this transistor in? Is it on? Well, it would make sense it would be on. If it were off, then the currents would all be equal to 0. I have 0 volts here at the base, and I would have 10 volts at the emitter, but then that means this base emitter junction would be forward biased by 10 volts, which makes no sense. So I assume the transistor is going to be on. The question is whether it is in active operation or saturation. Well, we'll check that, we'll make an assumption, and then we'll check and confirm our assumption to see if it's correct. So in this case, I'm going to use, once again, the constant voltage drop model. And VEB is equal to 0.7 volts. So this is the constant voltage drop model. Again, I'm assuming now, in this case, I'm going to assume the transistor is active, which hopefully is a good assumption. So let's go through and do our calculations for this. So we note, I don't know what VB and VE are, but obviously I know there's a relationship between the two of them. I know that VE must be equal to VB plus 0.7 volts because of the voltage drop, the constant voltage drop assumption. So this is my first equation. I also know that VB, just by Ohm's law, VB must be equal to 50,000 times IB. I also know that IE must be equal to 10 minus 2,000, pardon me, I should say, rewrite that, I should say VE is equal to 10 minus 2,000 times IE. And in addition, I know that IE will be equal to beta plus 1 times IB, which is equal to 101 times IB. And IC will also be equal to beta over beta plus 1 times IE. That'll be equal to 100 over 101 times IE. And now I can go through and solve for these equations, using Mathematica or just using standard substitution. But if I solve these, what I'll get is the following. I'll get that IB is equal to 36.9 microamps. IE is equal to 3.73 milliamps. IC is equal to 3.69 milliamps. VB will be equal to 1.85 volts. And VE will be equal to 2.55 volts. So I solve these, I get these solutions. We now also want to calculate VC, giving these values. And so VC will be equal to minus 10 plus 1,000 times IC. So taking this value of IC and plugging it in, I will get this is equal to minus 0.631 volts. So here's my solution. VB, VC, VE, IB, IE, IC. Seems to look good. Does it make sense? Well, let's take a look at this. So VB is 1.85 volts. VC is equal to minus 6.31 volts. So for this PNP transistor, VCB will be equal to VC minus VB, which will be equal to minus 6.31. Minus 1.85 will be equal to minus 8.16 volts. And clearly, this is a reverse biased diode. And so it's reverse biased. Base collector junction is reverse biased. Or I should say collector base junction is reverse biased. And therefore, my active operation is confirmed. Base emitter forward biased, base collector reverse biased. And again, I've mentioned this before, but one way of thinking about this is simply to think about the diode itself. So in this case, when we're looking at this is a PNP transistor, so I'm going to have a diode, PN diode between emitter and base. That's clearly forward biased. I'm also going to have another PN diode between the collector and the base. And clearly that one's going to be reverse biased, because in this case VC is going to be equal to minus 6.31 volts, and VB will be equal to 1.85 volts. And so clearly the anode is more negative than the cathode. That diode, or that junction, that PN junction, is going to be reverse biased. So it's always a way to think about it, okay? Not just doing the numbers, but think about that diode structure. Is it forward or reverse biased? Okay? So let's work another problem. Let us work a problem with an NPN transistor, but now I'm going to put in a different type of circuit in the base. So in this case, let's look at the following problem. So in this case, I've got an NPN transistor, and I am using a voltage divider here in the base. So both the collector resistor and the base voltage divider are both connected to 10 volts. This is R1, this is R2, this is 10 kilo ohms for both of these R1 and R2 resistors. And I've got RE and RC, and RC is 1 kilo ohm, and RE is also 1 kilo ohm. And again, in this particular example, it is given that beta for the transistor is equal to 100. And in this case, I want to find all three of the currents, IB, IE, IC. So I want to find IC, IB, and IE. Now, when you do a circuit like this with that voltage divider in the base, now when we had for a MOSFET we could put in a circuit like this, and the gate current's equal to 0, which means it would have no effect at all on the voltage divider equation, on the KCL equation for that base circuit. So IG is equal to 0 for MOSFETs, but unfortunately IB is not equal to 0 for BJTs, which makes this type of problem a little bit trickier than it is for a MOSFET. So let's go through and let's write the equations and solve for this. So I'm going to write a KCL equation for that base. And this current will equal to that current plus that current. So my KCL at the base, minus, let's call this, of course, VB, the voltage at the base. So 10 minus VB divided by 10K is equal to IB plus VB over 10K. I'm again going to use the constant voltage drop approximation for the base emitter junction. So again, I'm assuming I've got about 0.7 volts across that base emitter junction, and therefore there is VE. Therefore, VB minus VE must be equal to 0.7 volts. Or VE is equal to VB minus 0.7 volts. And again, that's the constant voltage drop approximation. And IE will therefore be equal to VE over 1,000, which is going to be equal to VB minus 0.7 divided by 1,000. And we also know that IE will be equal to beta plus 1 times IB, which will be equal to 101 times IB. And so again, I can now go through and solve for these equations. So in this case, what I'm going to get, I only need to, at this point, to solve for IE and IB. And what I will get is that IB will be equal to, if I solve, IB will be equal to 40.6 microamps. IE will be equal to 4.10 milliamps. VB will be equal to 4.80 volts. And VE will be equal to 4.1 volts. So solving these equations, I get this. I also can calculate VC. So in this case, VC will be equal to 10 minus 1,000 times IC. IC will be equal to 100 over 101 times IE. So plugging these values up here for IE, plugging into the equation here and substituting, what I will get is that IC will be equal to 4.06 milliamps, and VC will be equal to 5.94 volts. So I wanted to calculate IC because, of course, I also wanted to check and make sure that this transistor is actually operating in active region. Because, of course, I'm making the assumption it's in active operation. So that was my assumption. So now if I go through, plug in these values, here's IB, IE, and IC that I've calculated. But if I check my voltages, what I get is that VBC is going to be equal to, in this case, will be equal to, let's see, VB is 4.80 volts. 4.80 volts minus VC, which is going to be equal to 5.94 volts, which is equal to minus 1.14 volts. Again, the base collector junction is obviously reverse biased because of that negative voltage, and therefore active operation is confirmed. So this is one way of working this. And what I did here is I basically took all these equations. I can crank through the algebra, or I can just take this group of equations, I can plug them into a piece of software like Mathematica, of course, and just go through and calculate them that way. Let the computer do all the heavy hauling. But there's another way to look at these types of problems. And this is something the book shows, which is a more intuitive way of actually going through and solving for this type of problem. But you have to use Thevenin's theorem in order to apply it. So, although this works just fine, I can show you a way that gives you a more direct solution of the emitter current and the base current. So let's go ahead and let's do that. Let's take this circuit. And I'm going to partition this circuit, and I'm going to create a Thevenin equivalent of the base circuit on the right, or pardon me, on the left-hand side of this circuit. So I'm going to treat this transistor and these resistors like the load of a Thevenin equivalent circuit. So what I'm going to do is I'm going to Thevenize that input circuit. Let's go ahead and let's do that. So the Thevenin equivalent of that voltage divider so I've disconnected the load. I've got 10K, 10 volts, 10K. Well, first of all, having removed the load, what's the open circuit voltage? Well, in this case, it's very easy. I'm going to have this open circuit voltage VOC is equal to 10 over 10K, rather multiplied times 10K over 10K plus 10K, and that'll be equal to 5 volts. And so that's my Thevenin equivalent voltage. And my Thevenin equivalent resistance, well, there's a 10 volt source. I'm just going to ground that, set that equal to 0. So when I set that resistor equal to 0, I'll have this. And I'll say, what is this resistance looking in between ground and this node? Well, it's just 10K in parallel with 10K. And that will be equal to 5 kiloohms. So a very simple Thevenin equivalent circuit, right out of your first circuits course. But now I can take this and I can now apply this to that circuit I just drew, which is what I'm going to do. So now let's go through and let's solve for this circuit. Once again, I'm going to define my base current and my emitter current. So what I'm going to do here is I'm now going to write just a couple of equations that will let me calculate IE and IB. So in this case, once again, we're using the constant voltage drop assumption between the base and the emitter. So I've got 0.7 volts. And now this is 5 volts. Let's now go and let's write a KVL equation around this loop, around this base emitter loop. And what I'll get is that 5 is equal to, well, in this case, given the direction of the current, that's the polarity across this, that's the polarity across that resistor, and so 5 volts will be equal to 5,000 IB plus 0.7 plus 1,000 times IE. So I just wrote that simple KVL equation, and it's strictly in terms of IB and IE. And now I can say that in this case, since I know that IE is equal to 101 times IB, I can now just go and substitute into this equation, into that variable, into that term, and now I can just solve for IB and then also for IE. And so what I'll get is that IB will be equal to 40.6 microamps. And VB will be equal to 5 minus 5,000 IB, and that'll be equal to 4.80 volts. So once again, just the voltage drop across that resistor. And I'll get the same value for IE, because once again, comparing these values, 40.6, 4.8, so same values we got up there. And so therefore IE will be equal to, once again, just using this equation, will be equal to the same value we got up there, 4.10 milliamps. So you got exactly the same answer, which you should. I mean, the Thevenin equivalent gives you an equivalent answer, gives you the same numerical answer. But why did we do it this way? Why does the book show this way? Because when you create that Thevenin circuit and write that KVL equation and then apply the beta equation, it's very easy to very quickly calculate two of the most critical currents in the circuit, the base current and the emitter current. And once you know that, everything else falls into place with Ohm's law and with the beta equations. So doing it this way is not really necessary in the modern era. If you want to solve simultaneous equations, you have programs like Mathematica to do that for you. What it does help you to do is to visualize how to solve the problem. Do the base emitter loop first, solve and get those answers, and then what else you need to do will become very clear to you. So it helps you from getting lost in all of the equations if you just try to blindly start writing equations down. This is a way of actually helping you visualize how to solve the problem. You know, before the modern era of computers, this may actually would have saved you some time, made some calculations easier. Nowadays, that's not so necessary, but it still is a good visualization aid. All right, let's do another problem here. And in this case, I want to do something for our last problem where this is going to be more of a design problem. So once again, we're going to use a PNP transistor. So for our final example, we get this problem. Again, I'm using a voltage divider at the base. So I've got an RE of 2 kiloohms. This is 20 kiloohms, and this is 40 kiloohms. All right, so this problem is a little bit different. Given that beta is equal to 50 for this transistor, let's find the value of RC such that VEC, the voltage between the emitter and the collector, is equal to 2 volts. So this is VE, this is VC. I want VEC to be equal to 2 volts between the emitter and the collector. All right, let's solve this. Now, obviously, the transistor has to be turned on in order to have the voltage drop across that collector-emitter junction. So that's a given. The transistor's on, or it's going to be on. So in this case, we're going to go and, just as we did before, specify VB, IE, IB, and IC. And if we go through and write the equations for this, so again, do the KCL equations. I can write them like so. So for my base junction, for my KCL for the base junction, I've got that 12 minus VB over 20K plus IB is equal to VB over 40K. In addition, I know that I must have 0.7 volts between the emitter and base, so VEB is equal to 0.7 volts. So therefore, VE minus VB is 0.7 volts. And I know that 12 minus 2,000 times IE must be equal to VE. And I also know that VC must be equal to IC times RC. So if you were to take these equations and plug them into Mathematica, you'll quickly realize you're not going to be able to get a solution out of these because you don't know what RC is. But what else is given in the problem? You also know that VE minus VC is equal to 2 volts. That's the additional equation that you need. So if you now go through and you solve these, what you're going to get in this case is that VE is equal to 9.08 volts. VC is 7.08 volts, so VEC is equal to 2 volts. And in order to make this work, what we will get is that RC will be equal to 4.95 kiloohms. In addition, I also forgot to add here that we need to calculate IC. And IC in this case will be equal to 1.43 milliamps, which will be equal to, again, 50 times IB. So going through and calculating these, I now have my answers, and I have a value of RC is 4.95 kiloohms. So I wrote my equations, plugged them into Mathematica. So this gives you the answer. But again, sometimes Thevenin equivalent visualization can be helpful. Let's take that exact same problem. And let's Thevenize the base circuit. And so my open circuit voltage will be equal to, let's see, 12 times 40K over 40K plus 20K, and that'll be equal to 8 volts. So I have an 8 volt voltage source for my Thevenin equivalent voltage plus 20 in parallel with 40K, and that will be equal to 20K in parallel with 40K is equal to 13333 ohms, 13,333 ohms. And here's my R sub E. Here's my 12 volts. And once again, I have 0.7 volts between VE and VB. And so again, defining my currents, IE flows in this direction, IB flows in that direction. I define my voltage drops across these resistors. This is 8 volts. And again, I'm going to write a KVL equation around that loop. And if I do that, I get the following, that KVL, I'll get that 12 volts is equal to 2,000 IE plus 0.7 plus 1,333 times IB plus 8 volts. So that's my KVL equation going around this loop. And we also know that at the same time, IE will be equal to 51 times IB. And once again, as we saw before, this is now easily solved. I can substitute for IE and then solve for IB, and then what I will get, of course, is that IB is equal to 28.61 microamps. And then at that point, I can plug in the beta relationships and then get IE and IC and solve the rest of the problem. So this may be a more straightforward way to visualize. Convert the base circuit to a Thevenin equivalent, then you can write that KVL equation, and then IB and IE just drop right out. You get the answers that you want. So in this case, it gives us, once we know IB and IC, then in this case we can go through and given IC, we can calculate what RC needs to be in order to calculate IC. Everything comes right into place. So again, same solution, you get the same numerical answers, but doing it this way, Thevenizing that base circuit, can sometimes give you a more straightforward visualization to what the solution needs to be, which is one of the reasons why the book shows you how to do it this way. It can be, rather than just blindly writing equations and hoping you haven't forgotten an equation. This is a way of getting two of the most critical parameters solved right off the bat. And once you know IB and IE, everything else falls into place. Okay? So this concludes our discussion for DC calculations for BJT transistors, applying the bias equations, checking for active operation. Now that we've learned how to do the DC bias equations, our next step is we're going to start looking at how to use MOSFETs and BJTs to design amplifier circuits, which is really kind of what this class is all about. So that'll be next time.